Okay, I think we've started. Alright, we had some questions about graphing polar functions, so the first thing I'm going to do is kind of a cheat sheet for the types of polar functions you're expected to know. So, there are quite a few types. We're going to start with, let me close all of this. Alright, we're going to start with circles. So, if you look through the previous videos about polar functions, we see the relationship between these, so you know how to convert from one to the other. So, if we talk about the equations, the polar equations that produce circles, there's three types. One, where r equals some value of k, and k can be any real number, including 0. And essentially what it's doing, when you see this type of equation where it's just r equals some number, it's going to be a circle centered at the origin, where k, whatever this number is the radius of that circle. So I'll go through some examples later. Right now this is just kind of a cheat sheet of the types of equations. Another circle equation type is, we still have r equals k, but it's k times the cosine of theta, or k times the sine of theta. And when we have r is equal to k times the cosine of theta, this produces a circle that's symmetric to the x-axis. So if you folded the x-axis in half, the circle would match up. So it's symmetric to the x-axis. And then if r equals some number times the sine of theta, then this circle would be symmetric to the y-axis. So if you folded the y-axis in half. Now, sometimes there could be a difference in whether or not the circle is on the positive side of the x-axis, if it's this type, or on the positive y-axis, or the negative of each of those, and it has to do with the value of k. So if k is less than 0, meaning if k is a negative number, it's going to produce a circle on the negative x-axis for this second equation. For a third equation, if k is negative, it produces a circle who is symmetric on the negative y-axis. So these two have different circles than what this one is. So the original one is centered at the origin. These two are a little bit different. So up here, k equals the radius of the circle, but for these two equations, k is the diameter. And we'll work through some of those, and it'll probably be a little more clear about why that's true whenever we see them put into action. So I wish I would have brought my other calculator. Hope you can see this. Not sure. Let's see if I put a little line on, if that helps at all. So just ignore what was just on there. I was having a day. Now I want to go back. There we go. Alright, so what I've done is I've taken my calculator and I've put it on polar function mode. So I pushed mode, scroll down away from function, which is what we normally do whenever we work with this calculator, and we put it on polar mode. So I went and highlighted polar. I put it on degree mode right now, just so it's easier to see whenever we look at the table of values. So I'm just going to type in, see how it's not y equals anymore, it's r equals. So it's r equals instead of y equals, which is nice because that's the form of our equations when they're polar. And then theta is our variable. So instead of x, whenever we push our variable button, it ends up being a theta. So I'm going to type in a couple of these circle equations. So r equals k. So we already have our r equals. So r equals k. So what's a good number? 3. Oops. 3. Okay. There we go. So what this is doing is producing this first type of circle. It's going to produce a circle with just these two things, r equals 3. The circle is going to have a radius of 3, and its center is going to be on the origin. So, oh, I know. Okay, let's try that again. Oh, you see how it's lopsided, doesn't look like a circle. That's just based on what this is here. It's a 10 by 10, but because it's rectangular, it's looking like an oval instead of a circle. So I'm just going to go to zoom, and instead of a standard window, I'm going to choose the square window. So I'm going to push number 5. And then we can see that it is producing a circle. And the radius of this circle is 3. So now, let's say I take that 3, I leave it there. So we just saw that this produced a circle centered at the origin with a radius of 3. But now I'm going to type in 3 cosine of theta. And now when I hit graph, we're still getting a circle. This time its diameter is 3. Because remember we said whenever we type this kind in, the diameter is what k is. And if you notice, it's not centered at the origin, but it is symmetric to the x-axis, meaning if we were to fold it in half, we'd be able to, the circle would match up on the x-axis. So I'm going to go in and change this. The only thing I'm going to change is 3 sine of theta, and watch what happens. There's 3 sine of theta. If I go in and put a negative in, so now it's saying the diameter is -3, but think of what polar coordinates do when they're negative. So what's happening is it's just shifting that circle. So now it's on the negative y-axis. It still holds its symmetry. It has a diameter of 3, and that's what we're looking at there. All right, now let's go back a little bit, zoom out a little bit. All right, so that's our circle stuff. The next type that you need to be familiar with is a spiral. And these are really cool. The rest of these types of polar functions are really neat. So circles are pretty boring, but the other ones are going to be really cool. So you can produce a spiral by taking k, that k value, but this time instead of multiplying it by the sine or the cosine of the angle, it's just k times theta. So k times theta. And when we do this, k controls the tightness of the spiral. So the smaller the value of k, the tighter the spiral is going to be. So of course, I want to show you what happens. So, go away. So now let's just do 3 theta, and hit graph, and it produces a spiral, and it continues to go unless we gave it some sort of boundary. So let's compare that spiral, to a different spiral. So I'm going to make it a smaller r value. So I'm going to keep 3 theta there, and now we're going to do 2 theta. And let's see. So there's that 2 theta. See how it's a tighter spiral? And if I were to do 4 theta, what do you think is going to happen? So it's, again, creating a spiral. And if we were to continue to zoom out, you would see this is just, if you go, it's making it stop at a certain spot. So that's why it's stopping. But you can make it keep going depending on the boundaries that you set for theta. All right, interesting. So produces a spiral. All right, third type of polar function we're going to talk about is this fancy word. I am not French, so I'm going to mispronounce it. There's, I don't even know what it's called, a little like thingy here, limesson. So here are the equations to produce these types of functions, and this is a big grouping word. There's 3 different types that we're going to talk about. So it's a plus or minus. We still have k, and then we can say the cosine of theta, or a plus or minus k sine of theta. So obviously I'm just grouping these together. It's either going to be plus k cosine or minus k cosine or whatever down here. So it's never both. It's one or the other. And again, whenever we see these k values, and I should have mentioned it up here too, the spiral was symmetric, or it started on the positive x-axis. If k was negative, it would have started on the negative x-axis. Same thing over here. This is going to produce, these are going to produce certain types. So let me talk about that first. So essentially, whenever we're using an equation with cosine, it's always going to produce an x-axis symmetry, and a sine is a y-axis symmetry. So there's 3 types. There's 3 different scenarios here, and in each of them we're comparing a to k. Comparing to a to k. We ignore the subtraction sign for right now. What we're just looking at is the true values of a and the true values of k. So if a is less than k, this type of function produces a looped limesson. And I'll show you what I mean by that. If a is less than L, less for loop. If a is greater than k, There's lots of different words for this. It produces what I like to call a bean. It's a dented circle, or I'll show you. All right, and then finally, if A isn't less than or greater than K, the only other option, A is equal to K. When A is equal to K, it's a very special scenario. This produces a cardioid. That word sounds familiar. It produces a heart, a special little heart. So think of this around Valentine's Day. You can spend it or send a special little heart Valentine, math nerd style. All right, so let me show you some different scenarios of what I mean by this. So we're going to go back to the graphing calculator. And let's get rid of all these that are in there. So we're going to keep with this equation. So A plus or minus, and we'll start with cosine and of theta. So first scenario is when A is less than K. So I'm just going to pick a couple values. So let's say 2 plus, so I want A to be less than K. So K should be bigger to produce a loop. So let's look and see what a loop looks like first. So what about 3 cosine of theta, right? So let's see what happens. I need to reset my window, I'm sorry. Okay. All right, so again, sorry, this is awful. My theta steps here, theta is going through 2 pi. That's enough for right now. We can talk more about that later. But I do want to kind of zoom in, so I'm just going to have my x-axis go from -10 to +10, and then -8 to +8. Let's see if that's good enough. All right, so it's a little bit hard to see. We can show you on Desmos, or you can go graph this on Desmos if you want to, but it is literally producing a loop. So instead of making it a whole circle, it's producing a loop right there. So there's literally a hole. So it's looping around. Let's see what happens. What we're calling a bean. What are we calling a bean? So A should be greater than K. So what if I just change this to a 4? So 4 plus 3 cosine theta, what's going to happen? So see how it's a bean, or it's a dented circle? So it's not a full circle, it has a little dent in it. So we call it a little bean. Think of like a little bean. If you go and look at one in your pantry, they kind of look like this. So it's a little tiny bean. Now a lot of times people confuse this shape with a heart. So let me show you what happens whenever we're graphing a cardioid. So 4 plus 4 cosine theta. So do you see the difference? It's not a dent, it's a little divot. So it does come to a point there instead of just a little dent. So this is a cardioid. So let me reset this. There we go. Look at that. So it's a fat little heart. You can control the different kinds here, or the different sizes of it by controlling those two numbers. So let's look at what a cardioid looks like with the sine function. So that's an upside down heart. See if you can think of a way to make it a right side up heart. Right side up heart. What do you think is going to control that? Do you think we could change one of those values? So let's try, the easiest one to try for me right now is going to be change this to subtraction. Let's see if that does it. Wow, neato. It's a heart. It's a heart. How cute. Okay. Some other things to talk about here. So you saw when I used the sine function, how instead of being symmetric to the x-axis, it became this way, right, up and down, so it's symmetric to the y-axis. So again, what we're talking about here, sine controls, or the cosine and the sine controls which axis it has symmetry to. And then we could change its orientation by controlling the different signs. So see how we changed k to a negative, and then it flipped it so that it was down on the negative y-axis instead of the positive y-axis. I can't think of anything else to say about those right now, so let's go to the next type. Next one are roses. So roses have different types of equations, either k times the sine. So I'm going to introduce a new parameter here, b. Oh, sorry, I didn't. Okay. So r equals k times the sine of b theta, or we can swap that out. R equals k cosine b theta. Okay, so the symmetry in these is a little bit harder to see. It's not necessarily as explicit as the rest of these. So roses are a type of flower, right? And flowers have petals. So when we get an equation, a polar equation, and it represents a rose, we can tell how many petals the rose is going to have based on one of these two parameters, K or B. So B is the thing that controls it, but the rules are a little bit strange. It depends on if B is even or if B is odd. So if B is even, then your rose will have 2 times B leaves or petals, which is interesting, kind of weird. I'll show you what that means in a second. And if B is odd, it just has that many petals or leaves. And K tells you the length of the petal or of the leaf. So let me show you an example. I'm going to just get an equation and I'm going to write it out here. Let's do y. Why did I do that? R equals, and we'll do, I don't know, 3 cosine of 4 theta. So this is the equation for a rose. So one of your jobs will be able to identify which of these categories we fall into, and there's 5 main categories, so we've talked about 4 of them so far. So this is a rose because of the way the equation is set up. So the equation for a rose is K times the cosine of B theta, where B tells you the number of petals depending on if B is even or odd. So B is 4, which is an even number. So this rose should have 8 petals, right? If it's an even number, we double it to get the number of petals. How long are the petals going to be? That's what K tells us. So because K is 3, the petals are 3 units long. Let's see if we're right. So we have R equals 3 cosine 4 theta. Boop. All right, so what we're looking for here are 8 petals, 3 units long. 8 petals, 3 units long. Okay, so you can see it's a tiny little rose, but how many petals does it have? 1, 2, 3, 4, 5, 6, 7, 8. 8 petals. We don't want to count this one again. So it's 8 petals, and I know it's hard for you to see, but these are 3 units long. So again, I encourage you to use your calculator or to use Desmos. I'm going to send you a link that you can use to graph some of these. The polar graphing paper is already there for you. I can't produce that here. If I had a printer, I would print you one, but I don't because I'm poor. Okay, let's talk about this again. What if the 3 and the 4 were swapped? So let's say this time we have 4 cosine of 3 theta. So now B is 3. That's not an even, it's an odd. So if it's odd, you don't change the number of petals. It's 3 petals. Even if this was a sine function, it would still be 3 petals. K tells you how long the petals are, so K is 4. So the petals should be 4 units long. So this one will be a little bit easier to see if we are to graph it. 4 cosine 3 theta. Okay, graph. So how many petals do we see? 3 petals. 3 petals. How long are the petals? They're 4 units long. And again, difficult to see on this calculator. All right. So roses have a few other types of rules that are kind of complicated. So I'll go over those with you guys probably in a different video because I don't want this one to be 12 hours long like the rest of them. But we have one other type of polar function to talk about. And I'm going to pronounce it funny because I want you to remember it a certain way. Not that you would even know how to pronounce it, but anyways. So the 5th type is called so limnoscate, skate like the number 8. These actually produce figure 8s when you graph them. So they produce figure 8s, a limnoscate figure 8. So the equation for this looks really complicated, which is kind of good for you because they're the easiest to recognize. So we have, of course, the sine version and the cosine version. Sine version and the cosine version. Alright, so I'm going to show you what one of these looks like. If you see this, it's r squared equals this equation, but when we go to graph something, even if it was a regular function, if it was y squared, what would you have to do first? So we would have to take square root. So I'm going to say r equals the square root of 3 squared sine 2 theta. Alright, so obviously we could simplify this, but I want to see if we can make some connections. So let's see. We have the square root of 3 squared, 9, times sine 2 theta. Alright, and when we go to graph this, look at that. It makes a figure 8. It makes a figure 8. What if I just swapped out, the only thing I swap out is a cosine? What do you expect to see? Again, it's a figure 8. The slope is really steep right here, which is why we're kind of having some trouble interpreting it there, seeing the lines being graphed. But if we were to zoom in, we should be able to see it. Should be. Still, no, it's because of the way that this zoomed in. So if we were to look at Desmos, it'd be much easier to see. It's just the slope is too steep for it to graph right there. It's just being silly. Okay, so is there anything else I wanted to say about those? They look like a figure 8. They also have some pretty crazy rules. They still hold the symmetry. So cosine is symmetric to the x-axis, and sine is symmetric to, it actually has odd symmetry, which is something we could talk about whenever we look at them a little bit more. But it's not symmetric. Let's go back. Sine. I screwed this up, which is good because you can't see it anyways. Okay, so if you look at it, it's right in the light. This is the sine one. That's the one I typed in. 9 sine of 2 squared and 9 sine 2 theta. You can see it has odd symmetry. What does that mean, Miss Shaper? Go back and look in your notes. Odd symmetry. So it's not symmetric to the y-axis or the x-axis. It has odd symmetry, and there's a special reason for this, which we can talk about later. Alright, so hopefully that is going to be helpful for you guys. There's a ton of different types of these equations. And again, it's just your job to be familiar with what's happening in each of these so that you can easily identify. So like, I'll give you an equation, something like, I don't know, let's see if I can make one up and you can see if we can figure out what it is based on what's given. So we're going to always come back to this. Those aren't going to be far for us. Let's see. We've got, I'll just do 2 of them for right now. R equals 2 sine of 2 theta, and R equals -1 minus cosine of theta. So I encourage you to always have a format in mind. So what I like are the letters A, B, and K. Other websites, maybe even Study Island or the online textbook might use something different. But I like R equals A plus or minus K, and then whatever trig function you've got, so cosine of B theta. So if we look at this one, nothing's being added or subtracted to it, so it doesn't have an A value. Instead, it has a coefficient for K, and then it has a coefficient of theta, which is B. So this has a K, and a B. So when we go and look back at our notes, which one is it the most like? So it's not a spiral, because a spiral doesn't have a sine or a cosine in it. It's not a circle centered at the origin, because it has sine or cosine in it. What about this one? Could it be a circle? Maybe. So these are out, spirals are out, circles at the origin are out, roses. So right now we're sitting here and here. We have K, but ours has a B. Ours has a B. This circle, no B, just a K. This one does have a B, so we know that we found a rose. And again, I'm not bringing up this one because it's very easy to see that it's not going to be a figure 8. So this has a K and a B, it's a rose. So that's where we use our rose notes. So look at B. B is 2. 2 is even. This is a rose with 4 petals. How long are the petals? 2 units long. They're 2 units long. All right. Number 2, -1 minus the cosine of theta. So now, if we look back at our general rule up here, what do we see? Well, now we have something added or subtracted. So we have an A value. So A is there. And it's not just as easy, though, as stopping whenever we see we're landing right here. We're definitely one of these 3, so you should be able to figure out which one is it. So it's not as easy as saying, oh, it's a limison. You have to be able to tell us what kind. What is it? So let's go back. Each of these rules compare A to K. So let's look. A is -1, but really we're looking at the value, so A is 1. And then K is also -1, but again, we're just looking at what is the value, the absolute value of these. So A is equal to K. Which rule does that tell us? We've got a cardioid. So this one should be a cardioid. Alright, this one I didn't write it, but it's a rose. This one is a cardioid. Now, once we've determined what type it is, whenever we have a limison, we need to tell what type of symmetry it's going to have. So, because this is using cosine, it's going to have x-axis symmetry. So, we can easily check our work to see if we got this right. So, I'm going to type these in. We've got 2 sine of 2 theta. Let me make sure I've got this good. So that does produce a rose. How many petals? 4, and then their length is 2 each. So each of the petals go out a distance of 2 from the pole, from the origin. All right, now we've got the second one, which we classified as a cardioid, so -1 minus the cosine of theta. So think of what a cardioid is going to look like whenever I push graph. So cardioid is a heart. It's a heart. It's centered, or it's symmetric to the x-axis, which means that this one should be sideways, right? So it's going to be sideways instead of straight up like a heart this way. Okay, it's not going to be like this or like this. Okay, it's going to be sideways, but which sideways is it going to be? So this negative k value here has something to do with that. So let's look. Oh, wait, I just made a mistake because they're both negative. Oh, you can't even really see it. But here is the little divot. There's the little divot. It's just very difficult to see. So it looks like a little lumpy circle, but it's not. So I have to change the windows and it's going to look funky, but I'll do that for you. Let's do negative, and then the y, negative 3 to 3. I don't know. That's a little better. So you can see, little divot, little heart. He's a heart, right? And he just turned on his side. There he is. Alright. So, that's it for today. Hopefully that helped, because part of your job, I know, is, like especially on Study Island, is to be able to identify what type of polar function is getting graphed. So I'm going to send you guys some links more specifically about graphing them, and then I'm also going to work on graphing these particular functions, but just graphing polar coordinates. But if you're struggling with that, go back to the previous video, and I hope that helps. Okay, bye!